In example number 2, we got a transfer function that is like this. And based on the transfer function, we have no zeros, but we got two poles. Now, in general, a transfer function can be expressed in terms of what we call a standard form. So, the standard form are composed of factors, which we shall define later. Now, how do we then plot the Bode plot in terms of these factors? Well, what we do is actually plot each of the factors, so the magnitude and the phase Bode plots of these factors, and then to get the resultant Bode plot, we graphically add the Bode plot of each of the factors. Again, note that the magnitude plot, Bode plot, will be in decibels, while the phase angle will be in degrees. So, what are these factors? So, we will define 7 factors that appear in various combinations. So, for example, one factor could be simply a constant gain k. We also have j omega, or a 1 over j omega, so we call it a 0 and a pole respectively, specifically a 0 or pole at the origin. We also have 1 plus j omega slash z1, so we call it a simple 0, and 1 over 1 plus j omega over p sub 1, so we call it a simple pole. And we also have a quadratic 0 defined as shown, and a quadratic pole. So what do we do with these factors? So we plot each of these factors. We establish the how the Bode plots of these factors looks like. And once we establish the Bode plots of these factors, we then use it as a reference to plot the Bode plots of more complex transfer functions. Okay, so first, let's look at the constant gain k. So the magnitude mode plot of this is simply the log of the constant k times 20, which is actually constant, and the phase mode plot would be a 0 degrees because it is a constant. So the plot of this for the constant would look like this. So it is a constant. So as omega varies from a small value to a large value, the magnitude of the constant gain would be constant, while the phase angle would be 0 regardless of omega. Now for the 0 at the origin, so this is something that looks like j omega in the transfer function. So the magnitude Bode plot would be, again, by definition, would be log of the magnitude, which is omega. We times that by 20, so we got the magnitude in decibels. Now the angle of this is 90 degrees, so we get a phase mode plot, which is actually also a constant, 90 degrees. So the plot of this would look like this. So at omega equals 1, you will get HDB equals to 0, because log of 1 is 0. No? So 0 times 20 would be 0. And if omega is 10, you will get log of 10, which is 1 times 20, you will get 20. So you will get a 20 here. No? So it will actually make a straight line with positive slope. passing to omega equals 1 radians per second with a value of hd equals to 0 with a slope of what we call a 20 dB per decade. So there's a change in the gain of 20 dB as you move from um, one major divisions to another in powers of 10. On the other hand, the phase Bode plot, well, it is a constant 90 degrees regardless of omega. Now for the pole at the origin, since this is something that looks like 1 over j omega on the transfer function. So if you take the log of that, well, it is simply negative 20 log of omega. And the phase would be negative 90 because it is 1 over j. Now, if we plot the magnitude of this pole at the origin, you will get also a straight line passing to 1 omega radians per second with a value of hd equals to 0 and also a slope of 20 dB per decade, but this time it will be negative because of the presence of a negative sign here. Now for the angle, it will be a constant negative 90 degrees, regardless of the value of omega. Now in the next video, we'll be plotting the simple pole and the simple zero.